So I think we can start. Our chairman disappeared, but good morning again. And today I will try to show you some features which are used in most ritual analysis. And it's a little bit like the first part of the talk, a little bit like a travel in the sausage factory, So I will show you what is it in the sausage. So the second part will be more, say, special for using these methods. And so I will try also a little bit of a hands-on session with you. And sorry, I already started.
Go ahead.
And so I will... I encourage you to download the files that are in the school repository, and also for you to follow the presentations, this one and in the afternoon, since I see the screen is quite small. If you follow on the slides, it's more or less the same. Maybe there is a couple of extra slides. No. So all in all, download. This is for the tutorial, but this is the whole thing here in this zip file that you find the slides and files for the demo. Okay, so 2 days ago I have shown you some practical aspects and how to handle the instrumental resolution function. Then after this talk that was on the IRF, there's been the session given by Robert Dinnebier. I think he has shown how to do things in practice using Topaz. And so I'm not going to talk of the instrument anymore. Okay, so that's given. So we will focus more on the other part of the contributions to the line profile. Line profile is a convolution of effects, the instrument and what we call the pure diffraction profile, which is mostly related to the microstructure of the material. So what kind of information can we get? Well, we get information on the size of the crystals, typically, on the effect of defects, like it could be dislocations in plastically deformed materials, but it could be also be due to stacking disorder. Now, I will not talk much of stacking disorder, simply because I have no time for that, maybe a few minutes, but let's start from size broadening effect with a very, very simple picture of where it comes from. So let's think of a small crystal like this one. The crystal has a thickness d. You can think the thickness in the direction of the scattering vector, so direction that Bragg's law works. So this means that if you think of atomic planes, the peak is only produced when you are in Bragg condition, so at the right angle. At that angle, we know it happens that all diffracted X-rays are in phase. That means that the intensity is a big number because it's proportional to the square of the sum of the amplitudes of all scattered rays, which is a number of the order of the square of the number of the atoms. So it's a big number. That's why we see diffraction, right? And this is true in Bragg condition. But now, what happens when you're not in Bragg condition? So you take now an X-ray with a wrong angle, too low. It simply happens that this X-ray scattered by let's say, the surface of the crystal is going to be cancelled by another X-ray, which is a little bit inside the material. And so you observe no intensity. And if you do the same thing at higher angle, like here, the same happens. This one is also cancelled completely by another X-ray, which is just a little bit inside the material. So now, what if the X-ray angle is close to the Bragg condition, like here? Well, it simply happened that this X-ray will not be cancelled, not completely, because to be cancelled, you will need an X-ray which is out of the crystal, beyond the thickness of the crystal. So this X-ray will not be completely cancelled. And this happens for everything which is in between, let's say, if you see the colors, blue and green arrows, which point to the, say, zero intensity. And so you have a peak. That's the reason why the size of the crystal, the thickness, remember, thickness along the scattering vector direction, so perpendicular to the diffracting plane. This is the reason why we do see a broadening of the peak. And it is quite obvious that the width of the peak is going to be proportional to the inverse of the size. So the bigger the crystal, the narrower the peak, and vice versa. So what I've just explained with this simple example is what we call Scherrer equation, from the equation known since 1918. You know, Paul Scherrer was Peter Debye's student, and when he proposed this equation, there is a nice story about this equation, but I have no time for history right now. But it's just like this. You add a constant k, we will see what the meaning is, and this is the way it works. Instead of using a full width F maximum, you might also use the integral breadth, which is also, I guess, something that has been introduced. And it's just the area divided by the maximum intensity. So it's the width of a rectangle with the same area as your peak. It's another way of looking at the peak width. So let's use integral breadth. There are good reasons to prefer integral breadth, but you can do the same theory for full width F maximum if you like so. And so now the Scherrer equation is written same way. So still the width, now the integral breadth, is inversely proportional to the thickness of the crystal, d, and the constant is the Scherrer constant. What is the value of the Scherrer constant? This is going to be important also in the next slides. If you assume, for example, that your crystals are spheres, which is quite a common assumption, the coefficient is 4/3. And if you prefer, you can include the coefficient with the information on the thickness of the crystal, and this is what we call, with the symbol, Topaz, the software calls this L-vol. So if you use this L-vol instruction in Topaz, this is exactly what you're doing. You're calculating the thickness of the crystal divided by the Scherrer equation. And it's also interesting to note this expression as, you see, lambda over cos theta. Where it comes from, this factor of lambda over cos theta? It's very easy to understand. It's just if you transform things from 2 theta space to reciprocal space, which is inverse length space. So I don't want to spend too much time, but this is how it works, you see in this slide. Basically, it is just a transformation from 2 theta to reciprocal space. So in reciprocal space, the peak width, integral breadth, is just the inverse of these mean sides. But what is the meaning? And you see there is a mean symbol and the V that stands for something. The correct name of this thing that Topaz quickly call L-vol, it's volume-weighted mean column length. Ugly, long name. But because this is really very peculiar of diffraction. So let me try to explain what exactly is this volume-weighted mean. Now, you have to think a little bit differently now, okay? So let's imagine a crystal. Can you see the crystal and the atomic planes? Pardon me, this is not ChatGPT. I did it. So probably it's not the best. So let's imagine that you build up columns of unit cells perpendicular to the atomic planes, like this. Okay? Think of the entire crystal made up of columns of unit cells. The columns have a length L, which changes from point to point. Now, L-vol, the quantity you get from the software, from Topaz, from the Scherrer equation, is this integral. So you have to basically weight the thickness of the crystal along scattering direction over the volume of the crystal. So you see this is a volume integral. So the size you obtain from diffraction is not at all a trivial thing. It's not like you take TM pictures and you find the same stuff. This is a dramatically different quantity. There is another way to look at this problem. I like this. It's like when you make French fries. Why I'm talking French fries? You know French fries? I think so. So you take a potato and you slice it in this direction. These cones, think now these are made of unit cells. you can calculate a distribution of these columns. This is more or less how the distribution looks like. And this volume-weighted mean column length, it's averaged over that distribution. Okay? So it's quite complex thing, but just to tell you that it is not a sort of diameter of the particle. It's not so simple. It's volume-weighted. Okay, I hope I didn't shock you, but things are complicated. No way. Now, let's talk about strain effects, which is also a very complex issue because the information on strain from diffraction is quite very, deep. Now, let's start with a uniform strain. What happens if you take a piece of steel, for example, and you pull it? Of course, you increase atomic distances in the direction you pull it, no? So you add strain. How do we define a strain? Well, you take the differential of Bragg law and you rearrange them, and that's it. You shift the diffraction peak, delta to theta, which is the shift in the position of the peak, by a quantity which is proportional to a strain, where the strain is defined as the relative change or interplanar spacing. Basically, we use diffraction as a tool, like analogous to mechanical testing. Now our strain gauge, the way we measure strain, is the atomic planes. That's the idea. So what happens to a diffraction peak? As I said, it happens that if you have a uniform strain, the peak just shifts. You have a positive strain, the peak shifts lower angle. You have a negative strain, the peak shifts higher angle. Okay? Can you see this? This is just the effect of having a uniform strain in your material. So you can measure strain, and then with some constitutive equation you can work out the stress. This is a very practical thing. So now, what happens if instead of having a uniform strain, you have an inhomogeneous strain that changes from point to point? How could it be? It could be because you have defects inside the crystal, like these locations, which clearly have a non-uniform strain. But it could also be because grains in a polycrystalline material tend to, pull and push. Someone is in compression, some others are in tension. So you do not have the same, let's say, atomic distances and the same interplanar distances everywhere. So what you measure is this variable strain in the material. And then the peak broadens, because it's a little bit like having many diffraction peaks, sort of. So the peak becomes broader. So the same law, tangent law, is valid, because now it is not for the shift of the peak, but it is for the width of the peak. And in fact, we can write the same equation for the so-called half width at half maximum, which is half of the diffraction peak width, which is related to this E0 strain. I will tell you why I changed symbol, because things are more complicated than I'm trying to explain. It's a bit heuristic derivation, let's say. So, okay, easy. If instead of using the half width, we use the full width half maximum, there is a factor of 2, easy. So this equation is very much used to quantify the so-called microstrain. People use this name because this is not a uniform strain. It's a measure of how the strain is changing in the material. So it is related to the standard deviation of the strain distribution. So think of the strain varying in your material, like with a Gaussian distribution. The microstrain is related to the width of the Gaussian, which means the standard deviation. So it can be shown that if there is this kind of, distribution of strain, this E0 quantity is related to the standard deviation. It's also called RMS strain, root mean square strain. Okay? But it's not exactly that. The reason is because in this derivation, this equation is very much simplified. And then there are some things in between, in the proportionality, let's say. Okay, so now what do we got so far? two equations. One is Scherer equation. The full width of the peak gives you the effective size, okay? Is that L-vol thing I told you before. Then you have the other equation that the full width is also related to this microstrain term. So it is very human when you have two things, you say, oh, what should I do? Let's try to add them together. It's a great temptation. And this method has been used so many times and still very popular. If you rearrange this equation, which is just simply the sum of the two things, you rearrange them, multiplying by the cosine, you can make this nice plot called the Wilson plot or method. And from the intercept of your data, you get the size of the crystals, and from the slope, the microstrain term. This is so popular. I want just to stress 2 points. First of all, this exact assumption is used in most softwares, Topaz included, when you use the default double void approach, which I am going to show you in the next slide. That has been demonstrated by Roberts, and it's used not just in Topaz, but nearly every other Rietveld software do more or less the same. So this equation is hidden. Now you are in the factory, in the sausage factory. So you're looking at what is it inside your code. But the other point of interest is that this is totally arbitrary. So be careful. For example, why adding them linearly and not quadratically? Or in other ways, you have two phenomena. Why you just simply add them? There is no reason for that. There is no theory telling you add them linearly. And actually, linearly adding, it's wrong. Now, wrong doesn't mean that it doesn't work. It works. But the meaning of the parameters that you get is not well defined. So you can use it, and it will work well for your data, but just you have to be careful in the interpretation of the results. That's the message. So now let's go step forward toward Rietveld and what is in Topaz. I talk of Topaz because it's the best software I can use for these things, but it is not just Topaz, any other Rietveld. This is the double void approach. And let me introduce the void or Voigt function, as we should call Mr. Voigt. It's a linear combination, is a convolution of a Lorentzian and the Gaussian function. Now, x here is any kind of distance from the Bragg position. It can be to theta, it can be reciprocal space, whatever you want. Beta is the integral breadth, that is the Lorentzian and the Gaussian terms. And you can get the Voigtian integral breadth using these formulas here. Now, if you take this definition of the Voigt function, the double void assumes that you can deal with the size and microstrain effects using a convolution of two Voigtian. The nice property is that if you convolve two Voigt function, you have another Voigt function whose Lorentzian and Gaussian components combine this way. The Lorentzian is linearly adding the integral breadth. The Gaussian component is adding them quadratically. So up to this point, if you don't see the rest, the second equation, this is just a definition of the function, how it works. The next step is you use the equation from Scherer and the other one, linearly combined with the Lorentzian component and the Gaussian component. It is nice, it fits often your data, but the meaning is not very clear. I mean, you have seen that the meaning of the sites, it is not at all a simple one. And the strain even is even more dark meaning for this proportionality with respect to the real root mean square strain. However, to be practical and pragmatic, this is how you use the two equations in Topaz. And then what you get is this L-vol, which is the number you read here, is 21 nanometers in this example, and the microstrain, which is something in the order of 10 to the minus 3, okay? Now, let's be practical. I am a physicist, but I've spent the last 40 years in the Department of Engineering. So I can tell you what is reasonable and what is not. So a microstrain in the order of 10 to the minus 3 makes sense. If it's 10 to the minus 4, it's very, very small. 10 to the minus 5 is 0. And 10 to the minus 2 doesn't exist, or it is hardly possible. Okay, so this is just to give you an idea of what makes sense. Now, let's remember always about the microstrain, as I told you before, that it is proportional to the real root mean square strain. And you can find simple theories telling you what the proportionality factor is. This, for example, goes back to the work of Art Wilson in the 40s of the past century, so it's well known. But the problem is this assumption, it's quite limited because it's valid if your microstrain is uniform in your material, which is clearly not the case of a dislocation, the grain boundary strain. So it is nice, you can use this factor, but in the end, you try to be too much precise and accurate on something which is not. So in the end, nobody uses this factor of 1.25, or say, few people do that, just because the very meaning of this mean strain, it's not so much defined. However, so just a practical thing for those using Topaz, because this is a school where we are supposed also to use the software, and the hands-on session is what I will do. In the instruction, there is this coefficient 1 that must be 1. If you change that, you basically change the theory, and then you don't want to do that. So keep that number 1 fixed. This gave me quite many headaches before understanding that, because the sausage factory was not open yet for me, so I couldn't figure out what the meaning was. Okay, guys, let's see a practical example. I like this one. This is kindly provided by the ICDD, and Tom knows I am a fan of the PDF 3, which is that section of the PDF where you also have the data of the records, and even, like in this case, a TM picture and some information. So I just picked up the data from there, and these iron oxide nanoparticles are said to be in the order of 7 nanometers in size. This comes from the database. So we model this using Topaz, and as you see, the upper part is background and other things we don't care about. The structure is very simple. As you see, the iron atomic coordinates and oxygen. So this is the structural part above. And L-vol giving about 7 nanometers. This looks comfortable. If you feel good, say, oh, good. It's like the TEM. I would call this a pure coincidence somehow, but in fact, this is L-vol. So at least if it is said they are more or less spherical, you should use the coefficient from the Scherer equation, the 4/3 for spheres. And if you do that, the result is more in the order of 9.5, actually. So, but still, it's a reasonable agreement, and there is no microstrain. The data quality is not very good, but since this is not my data, I can blame the guy who did it. Now, let's be serious. Nanocrystalline materials is not always easy to have good quality data. So it's one of the reasons we love beam lines like the one Max talked about, like ID31 and similar. Okay, let me show you another example, which is in the files you can download, so for the tutorial. And this is a fluorite, so a very common mineral that has been ball milled. When you ball mill materials, you basically reduce the size and you introduce defects. And primarily in this kind of materials, you introduce these locations. So you can see them in the TEM. And the TM tells you that more or less the size of the crystalline domains is in the order of 10 nanometers. This is frequent in ball milled materials. So how did the double void approach work? It worked this way. It gave a not bad fit, not bad. I like to use the square root intensity scale because this is coherent with the weight of the data, if you remember from my previous lecture, you know that the standard deviation from the counting statistics goes with the square root of the counts. So using the square root in the intensity puts the data on a sort of fair basis, you know, higher counts and lower counts. And to be honest, they always look better. It's a little trick. So you always want to look into linear, square root, and logarithmic. Don't fool yourself. I mean, but square root is fair for the counting statistics. So what is the size? Again, now we got the 21 nanometers. And if we use the coefficient for spheres, well, things are not so beautiful. 28 against 10. So you see there is something going on here. There are some problems here. Let me show you two more examples, because this might be just bad luck, something gone wrong. You don't want to believe in things only for one sample. This is another sample which is calcite. If you grind the calcite in the right way, it is still calcite, doesn't phase transform, and goes down to more or less same size, 10 nanometers, with evident dislocations as well. So it's more or less like before, but it's not cubic material, and so it's more complex material. Now, again, this is the fitting. Now, first of all, we see the size. It's, again, not exactly the correct one. 30 nanometers against more or less 10, according to TEM. We also see that it doesn't fit perfectly well some of the data, some of the peaks. And I can already tell you that this is a matter of strain anisotropy. That's the topic I'm going to talk just after this. One more case now, a metal, and these are data similar to those you find in the folder. In the folder you can download. Now we know that here this is going to be full of dislocations after grinding. It's been heavily plastically deformed. And this is how topaz behaves. Now, we clearly see it doesn't behave very well, because this is iron alloy. Iron is highly anisotropic. So if there is strong strain in the material, the broadening will be different along different direction in the crystal. So we know, for example, iron has a stiff direction along the 111 direction. This is the stiff direction of cubic metals. Whereas it is more soft, more compliant, we should say, along the cube phase direction, so the 100 direction. So what do we expect? The 111 peak will be narrower, because for the same stress, there will be less strain, and the 100 peak will be broader, because they are more compliant, so they deform more. And in fact, this is exactly what happens. You see some peaks here are broader, some other are narrower. So this is clear sign of anisotropy. But on top of this, you see the size again is wrong. It's overestimated. So from L vol is 26. You add the size, the shape factor is 35, and the TM tell us no. This must be in the order of 9 nanometers. So let's talk of strain anisotropy now, which is something I think is of interest. It's also in the title of my talk, if I'm not wrong. So how do you deal with strain anisotropy? This is something you can do with Topaz and many other software. So first of all, I will show you how you do that with Topaz and other software, which sort of works, okay, but with little troubles. Okay, so first, you recognize that strain anisotropy comes from the anisotropy of the elastic medium. All materials are anisotropic. So elastic modulus changes along different direction. This is the expression of the elastic modulus for a single crystal with the cubic structure. You can write down the same equation for any kind of even triclinic crystals. For cubic crystals is easy. You see, simple expression involving the Miller indices and the Cij, which is in this case the stiffness tensor components. But for a cubic material, it's just three numbers. From these 3 numbers, you derive Young modulus, Poisson ratio, or what you want. But this is for single crystal. If you want to have a look at the anisotropy of iron, you want just to plot this function along the three spatial directions, and this is the shape, and the distance from the center is proportional to the Young modulus. So if you move along the cube phase direction, this is the Young modulus along 100 direction. If you move toward the corners, this is the 111 direction. So here you see the elastic modulus is much higher along 111, as I said before. Iron is much stiffer along this direction, and is more compliant along the 100 direction. So this is the reason of the anisotropy. Actually, this is not the entire reason. That's the problem of the method I'm going to show you. This is related to the anisotropy of the elastic medium, but defects are also geometrically anisotropic, because, for example, these locations do not just lie randomly on atomic planes. They tend to be on some specific high-density planes with specific high-density direction. So in addition to the crystal anisotropy, which is in this equation, you should also include the defect anisotropy. And which defect? Well, it depends on which defects you are dealing with. So this approach is good, but it's not complete, is not going to work perfectly well. However, Young modulus, I have no blackboard here, but you know, I assume you know Hooke law. Hooke law is known to everybody. Elastic strain, sigma, elastic stress is proportional to elastic strain, sigma, epsilon, in between E, Young modulus, okay? So sigma is equal to E times epsilon. So if you want to work out epsilon, it is going to be inversely proportional to the Young modulus. Okay? So this is the inverse of elastic modulus, and it can be demonstrated that it is related to this E0 quantity, which is the root mean square strain. So this is exactly what has been done by a couple of colleagues in the past. One of them is Nikolai Poppa, who has been the one who devised this idea, and then later by Peter Stephens, who has also inspired, let's say, what is it in topaz nowadays. In fact, you see the instruction, the macro is called Stephens, cubic because iron is cubic, but you can use for any other symmetry. And then basically you are adjusting the coefficients which are the elastic constants. So in principle, you might write down an exact number, but more empirically, you try to refine, adjust those two parameters. That's called PRM S400 and PRM 220. But basically are a combination of elastic constant and indeed the effect of the geometrical anisotropy of the defect. So you can use this equation instead of the E0. Sorry, I made a mistake, a terrible mistake. What's happening? Oh, okay. I pushed the wrong button. Okay, so instead of using E0 here, you use this Stephens equation. Let's see how it works, okay? Very practically with the previous data. This is how it works. Now you see that it improved considerably the peak modeling. So the narrow peak are narrow, the broad peak are broader. So it works because more or less the main source of anisotropy is the elastic medium somehow, and that equation works. Unfortunately, and even, oh, look at this, the RWP and the goodness of it improved a lot by 50%. When you work with Richter refinement, this is a huge improvement, not a small one. So it's great news. But still the size is wrong. You see, the size is 26 nanometers, a bit smaller, but it's still way beyond the real one. So the question is, what's going on? What's wrong here? Okay, so now let me tell you what's wrong. There are two things which are wrong. Now, let me define wrong first of all, because otherwise there will be a long list of people mad at me and say, oh, you want to destroy software, you want to destroy Rietveld and things. No. So please keep using double void and be happy with that. As I said, just be careful with the interpretation of the parameters. Reason why interpretation might not be so obvious and sometimes wrong is point number one, pseudo-void functions are intrinsically inappropriate to modeling the size broadening. Actually, they are also inappropriate for the strain broadening, but for the size broadening, this is strikingly clear. It's real evident, I will show you. The next problem is what size is really obtained using Scherer equation. I told you this strange volume-weighted quantity, which is maybe clear up to this point if your crystals are all the same size. But what happens if the size is not the same, which is always the case in real materials, okay? So let's see now these two weak points of using pseudo-void or whatever other analytical function. So first point, if you use even the most fancy version of a pseudo-void or void function, this is TCHZ, great, good idea and solution for Rietveld, but they happen to work well with the experimental data, but interpretation is very arbitrary and sometimes it is clearly wrong. So what's going on? For example, we just talked about this column length distribution. You remember the potato sliced in French fries. Now, think of a spherical grain, okay, which is not a spherical potato, okay? You can work out what is the column length distribution. It's this red line here. Very simple. It's easy. It's a pure geometry. It's simple. So this is the column length distribution. This is a distribution function. Every well-behaving distribution function is definite positive. Cannot be negative, right? I'm talking in general. And it must be 0 and 0. There is no column of 0 length. Okay, these are two very basic features. Now, you don't like a powder made of identical spheres? I can show you the same distribution if you have a log-normal distribution of spheres, which is something practical. In this powder sample, there was, you see, tiny things are nanocrystals, more or less 4 nanometers size, but they are log-normally distributed, so they do not have the same size. In the bottom corner, sorry guys, if you're far from the screen, you're not going to see anything, but believe me, this is a histogram produced using TM pictures. So it shows you what is the distributional sizes, and it is about centered in 4 nanometers. However, the important thing, this is the column length distribution. You see, it's not terribly different from the sphere case. It is just a tail, but still positive, 0 and 0. Okay, so keep in mind just this. You change the shape of the crystal, okay, it changes a bit, but still positive, 0 and 0. Now, you can mathematically work out what the size distribution is if your line profile is a Gaussian. It can be done. I'm not telling you what you need to do. You need to use Fourier transforms. Don't know Fourier transform at the moment, but it can be mathematically calculated, and this is it. As you see, is negative in some region. This is disappointing. It means if you use a Gaussian line profile, you cannot model the effect of broadening due to the size of the crystals. Full stop. Nothing else to say. Gaussian, it's wrong for many other reasons, but this is one. Now, what about the Lorentzian? The Lorentzian are also wrong because the size distribution is an exponential, so it doesn't start 0 from in 0. So you clearly understand that using Lorentzian and Gaussian line profile, or a combination of them, is intrinsically wrong because they simply do not have the property to describe a distribution which must be positive and 0 and 0. Okay? So it fits your data, but the number you get, be careful. Okay, so this is the takeaway message, very soft, so nobody is going to kill me for what I'm saying. And I am myself using a pseudo-void pen-box function. This is not a crime. Now, a bit more into, let's say, theory. what is the meaning of the Scherer equation? Let's have a look, because so far what I've shown you and what is used in the double void approach, so in Topaz as in many other softwares. So please don't make me blame Topaz, which is the software I prefer. It's Topaz like many others. Okay, so is this monodisperse system. So it means that if you now plot the distribution of sizes, so these are not columns, the size of the crystal. Imagine you have spheres in your sample, sphere with a diameter d. So if all spheres have the same diameter, the distribution is a delta function, right? Now, if you use the Scherer constant for a sphere, what is L vol? If you have this kind of sample, you see about, 8 nanometers size. L vol will be smaller because it is the size divided by 4/3. So it's a bit smaller. So this is the thing that we calculate. So the question is, okay, sorry, it's been too fast. So you use Topaz, L vol, and what you get is a number that is a bit smaller than, say, the true diameter of the sphere. If you believe your crystal are all sphere, all of the same size. This is mathematics, no discussion. Now, real cases, you hardly have the same size. Let's imagine you have a distribution of sizes. For example, this is a log normal. So the point is Scherer equation still valid? Good news, yes. What is the meaning of the size you get? Not so good news, because it becomes complicated, even more than before. Let me show you, because fortunately, it ends up in just a formula, so we can handle this. 10 minutes. So the thing involves now distribution moments. What distribution moments are? First moment is the mean. Second moment is related to the variance, and on and on and on. Okay, you comfortable with this definition? This is the definition of distribution moments. Now, we have to look at this strange combination of moments. Fourth moment divided by third moment. Let me call this lambda. And this is what L vol is. Now, the Scherer equation is valid for this strange ratio between fourth and third moments. Okay? So, you see, things are complicated because now the shape of the distribution has an effect on the meaning of the size you are measuring. Let me show you some practical example. Now, with this distribution, now, the mean that for some reason maybe you would like to compare with other techniques, microscopy for one, it's smaller than L vol because the distribution is skewed to larger sizes. But if you have a narrow distribution tending to a delta, it's the other way around. So you see how it is easy that you can overestimate or underestimate the real size just because of the effect of the distribution. If the distribution is very narrow, L vol will be smaller than, let's say, the true size. But if your sample is more dispersed, more sizes, it will be the other way around. L vol will be bigger, and it can be even much bigger than the true size. It can be 3-4 times bigger, as we have seen in the previous example. Okay, so the takeaway message is, forget these other slides because it's too complicated. Do not say that this quantity is the mean size. This is not the mean size. It is this kind of ratio between the moments of the distribution. Okay, so last step. There are problems in interpreting the pseudo-void parameters in terms of size and strain. This is, let's say, the conclusion of this thing. I would like to dedicate the last 10 minutes or so with the first part of a hands-on session, but I will do this just using my own data. Then you can repeat it with the data you can download, and maybe in the afternoon we go over another similar example together. So I will be extremely brave doing that because usually things don't work easily when you do this way, but I will try. So let me see. Okay, these are data from argon synchrotron. So otherwise it seems we only know one beamline.
We don't see it.
You don't see anything. Okay, I think I know why you don't see anything. Because I have to stop this. You see something now, right?
This is what we see.
Okay, good. This is what you have to see. This is the input file for this data from 11 BM. And it's very simple topaz file. So forget about the instrument, because the instrument has been already arranged. And here you see iron, ferritic iron, cubic, one atom, and then L-vol and E0, the two instructions we just talked about. There is a little tiny fraction of austenite. This is the other polymorph of iron. Forget about that. It's like 1 or 2%. But with Rietveld and topaz, you can handle as many phases as you want. So we can be quite precise. So if you use JEdit, I still use JEdit and not yet the other, forgot the name, edit, which is advised for topaz. It's easy because if you organize it the way John Evans shows, you can find the YouTube instruction, you can just click this one and this, and you transfer this input file to topaz. So let's load the data, and here it is. This is a portion of the diffraction pattern from the synchrotron. So let's start from a rather flat baseline background and some initial parameters. It is very fast because topaz is fast, and this is the results we get. So you see there are the problems here with the peaks that you see that the residual is not at all good because of this anisotropy we talked before. So let's see the result here. And what we get, you see 27 is more or less the same numbers you've seen in the slide. So it should be in the order of 9 nanometers, but it is not. So what can we do to improve things? We use this Stefan instruction. So you basically comment the strain model and you uncomment the Stefan instruction. Just a detail, but it's important. It's written also in Robert Dinebe's book that the coefficient of this function must be positive. Well, let me say actually this is not necessarily true. So for the moment, let's keep minimum value to 0. So the two coefficients must be positive. In the true life, they can be positive or negative, but okay, don't worry, not a big issue. Now let's try this thing. So what should I do? I save the data and go back to topaz, load these initial parameters. Now, of course, they're wrong because it's the starting value for Stefan's model. Run it, and you see now the residual is much better, is much flatter. So the good news is it works. It fits the data reasonably well, right? But now let's look at the parameter file. Okay, so let me transfer the parameter file, new file. You see the L-vol is still 19, so it's still way larger than it should be. And then let me comment about this instruction from Stefan Cubic. What use are you going to do of those three numbers? Nothing. They just help to fit the data, but there is no physical meaning in those data. And in my opinion, as a physicist, this is not something I'm going to accept. So I like it, I recognize it is very good, but in the end, I don't like it. I also want to add something that to be practical and fast in topaz, this instruction from Stefan models, Stefan model, in the end uses another pseudo-void. So the problem with the peak shape are always there. You're only treating the peak width better because you recognize some peaks narrow, some others are broad. But the profile function is still, let's say, not the best you could use. Okay, so this is the practical example. And if you read the tutorial you can download, you can do the same for all the other cases I've shown. And this, I think, is particularly convenient. Now, I guess we are only left with 4 or 5 minutes, right?
2, 3.
2, 3. But I started the countdown this time. Okay, don't worry. I am in between you and the lunch, so it will be 2, 3 minutes. I know how dangerous could be to stay in between you and the lunch. So let me just say that we need to change something, and I will just present you the general idea. Then we go in the detail in the afternoon with the hands-on examples. So this is what I did about 25 years ago. And it took a little while to be accepted by the community. As with all the good new ideas, you have to wait for the old guys to die before they are accepted. That's it. So as soon as you have a good idea, you have to wait me to die, which is, scientifically speaking, is not going to be too much long term, because I will retire not too many years since now. So what is the idea? The idea is to consider, as we have seen before, that diffraction peak is a convolution of G component instrument, F component the microstructure. Now the variable you read S is the inverse of interplanar distance. Now I'm definitely writing everything in reciprocal space units, so inverse length. So capital S is the distance in reciprocal space from the lower condition, let's say Bragg condition, because we're talking of powder. So what has been the idea of the method I have proposed? Say, well, okay, the instrument is a convolution of Fx, all the different components in the instrument. Let's assume it is the same for the microstructure, which is not exactly true, because these things are not independent. The size, the strain is actually all combined in the material, but this is a decent first order, approximation. So the idea is to use the fundamental parameter approach we know very well from the instrument, and this convolution of microstructural features for the microstructure. So S stands for size, D for distortion, deformation, so the strain, F stands for faulting, but then you might have other things, the relaxation of the surface, you might have inclusions, you might have antiphase boundaries. All the things might contribute to the line profile. And in doing this, we use the convolution theory. Here is where you need a little bit of mathematical knowledge. When you have a convolution is mathematically ugly to code into the software. A lot of headaches if you're not Alan Coelho. If you're Alan Coelho, you can do it. But if you're not, it's headaches. So the simple way of facing the problem of convolution is to use a Fourier transform. Because a Fourier transform turns convolution in a product. So multiplication are easy by definition. So the approach I took is to use Fourier transform, and then the convolution becomes a product. Now, the question is, who gives you the Fourier transforms? And this is definitely something I'm going to show you later. And you will see that we have reasonably simple expression for all of those Fourier transforms in terms of physical parameters. So there will be no other Stefan models parameters that fit the data, but you don't know what the meaning is, right? There will be physical meaning to all of them, and I will show you also in the demo. That's it. Thank you.